So we've mentioned that a lot of the stuff that we learned in the last chapter is going to be used for this next chapter, which is curve sketching. And so after this chapter, we'll have an exam that will encompass what we learned in chapter 4, extreme values, and this chapter, which is sketching curves. One valuable tool for sketching curves is to find the intercepts of the functions. To determine the x-intercepts, we let y equals 0, then solve for x. To find the y-intercept, let x equals 0, solve for y. So you've had experience before where you found the intercepts for a quadratic. The x-intercepts, if they exist, are always found by, again, letting y equal 0 and then solving for x. And we often do that by factoring. So this quadratic could be factored. Two numbers that multiply to get negative 32, add to get positive 4 would be positive 8 and negative 4. And then the x-intercepts are the solutions. They are where each factor equals 0. So they are at negative 8 and positive 4. Now the y-intercept is where x equals 0. And if you let x equal 0, those first two terms will become 0. For a polynomial function, the y-intercept is always the constant term. If you let x equal 0, those first two terms will be 0. You're just left with negative 32, or 0 minus 32. Okay, question 2. Again, our x-intercept is where y equals 0. So it's where the quadratic 3x squared minus 5x minus 12 equals 0, which we can solve again by factoring. The front terms multiply to get 3x squared, so it's 3x and x. The last terms have to multiply to get negative 12, and when we FOIL this out, we have to get a minus 5x in the middle. So I think that'll work with 3 there and a 4 there, because you'll have 9x and 3x when you multiply the outer and inner terms. 9x and 4x, I should say. And the difference between 9x and 4x is 5x. Because we need a negative 5x, the 3 has to be negative, the 4 positive. That will give us negative 9x plus 4x, which gives us the minus 5x in the middle. So there's the factors, and again, the solutions come when each factor equals 0. So for that first factor, you'll subtract 4 from both sides and divide by 3. The second one, you'll add 3 to both sides. So there are your x-intercepts. And again, the y-intercept is the constant term. In this case, negative 12. Number 3, again, our x-intercepts we'll start with. It's where the function equals 0. And the front terms will multiply to get 8x squared, so we'll try 2x and 4x first, and if we can't get that to work, then we'll try 8x and 1x. So again, the last terms multiply to get negative 15. So it ought to be 3 and 5 and or 15 and 1. When we FOIL it, we have to get a plus 2x in the middle. So if we tried the 3 there and the 5 there, the outer products would be 10x, the inner products 12x. So they do differ by 2x. Because it's a positive 2x, that would mean the 12x has to be positive, the 10x negative, and there's your factors. So again, the x-intercepts are found where each factor equals 0. That'll be at -3/2 and +5/4. So sometimes the x-intercepts are rational numbers. And the y-intercept is, remember, the value of the constant term, which is -15. Now the next one is a rational function. We find the x-intercepts by, again, letting y equal 0. But in this case, you have a rational function. And a rational function will equal 0 when the numerator equals 0, because 0 over anything is 0. So again, this is where the numerator, the top expression, equals 0. So the factors there are x plus 3, x minus 2. So x will equal -3 and +2. The y-intercept is always where x equals 0. In this case, there is no constant term. There is no one constant term, but there's a constant term on the top and the bottom. So when x equals 0, you'll just have -6 on top and -2 on the bottom. -6 divided by -2 is +3. So the y-intercept would be at +3. And we haven't been writing the coordinates, but this is where x equals 0. So there's your y-intercept at 0, 3. The x-intercepts are where y equals 0. So both those numbers are the x values, the y is 0. Okay? A few more to look at. Number 5 cannot be factored. If you want to solve the quadratic x squared minus 2x minus 5, we want to know where that equals 0. It cannot be factored. So that's where we use the quadratic formula. Remember, that's -b plus and minus the root of b squared minus 4ac all over 2a. So remember, your values of a, b, and c come from the coefficient. A is the coefficient in front of the x squared, b is the coefficient in front of the x, and c is the constant. So the value of b is -2, therefore negative b will be -2, which is +2, plus and minus the root of, again, all of b, the -2 is all squared, minus 4 times a, which is 1, times c, which is -5, all over 2a, 2 times 1. So -2 all squared is +4, and -4 times 1 times -5 is +20, so you're going to get +24 under the radical. And again, that's all over 2. Now this can be simplified because root 24 is root 4 root 6 or 2 root 6. You must do this if you want to simplify the expression, because in the previous step, sure, there's a 2 on top and a 2 on bottom, but in order to cancel, you have to be able to cancel the same factor in all 3 terms. And to do that, you've got to get the root 24 and break it down to a mixed radical, which we've just done. And now we can divide everything by 2, and we'll get 1 plus and minus root 6 over 1, or just 1 plus and minus root 6. So there's your x-intercepts. The y-intercept, again, is a constant term, in this case, -5. Number 6, again, cannot be factored. That one cannot be factored. So If we're going to solve it, we'll use the quadratic formula. Negative b, well, b is negative 3, so the negative becomes a plus positive, so it's 3 plus or minus the root of b, which is negative 3 all squared, minus 4 times a times c, all over 2 times 1, 2a. So this will give us 3 plus or minus, and now when we do the radicand, which is the number under the radical, negative 3 all squared is 9, it's going to be 9 take away 24, which is negative 15. And because you cannot take the root of a negative number, there are no solutions. There are no x-intercepts for this graph, which means that the vertex is above the x-axis, right? We know that this quadratic opens upwards because the initial term, coefficient, the number in front of the x squared is positive. That means the quadratic opens upwards. The fact that there's no x-intercepts means that the vertex is above the x-axis. It never crosses the x-axis. And our y-intercept, again, is the value of the constant term, which is positive 6. So these next examples are cubic functions, third degree. And to find the x-intercepts, we need to factor. And remember that we start with the constant term of positive 6. So we have our potential integral zeros. They are factors of the constant term. Plus or minus 1, 2, 3, and 6. So if positive 1, if we want to check to see if positive 1 is a 0, we would divide by x minus 1, but we'll change it to an x plus 1 so we can add as we're going along here. That's being divided into 1x cubed minus 2x squared minus 5x plus 6. Remember, when you're using synthetic division or long division, you need to have the polynomial written in order of descending power, highest to lowest. And if there's any missing terms, any powers missing, you include them with the coefficient of 0. So this one already was in the right order. There are no missing terms. You started with an x cubed. We've also got an x squared, an x, and a constant. So there's no missing terms. So leave a space, draw a line. That first coefficient is copied down, and then we multiply and we add. 1 times 1 is positive 1. We add and get negative 1. 1 times negative 1 is negative 1. We add and get negative 6. Negative 6 times 1 is negative 6. We add and get a remainder of 0. So in this case, we found it on our first try. That plus 1, really, remember, was x minus 1. We changed it to x plus 1 so we can add as we went along. And the quotient, the numbers at the bottom, give us the coefficients of the other factor, which will be a second degree polynomial because we divided an x cubed by an x. So it'll be x squared minus x minus 6, which that quadratic can be factored. Factors would be x minus 3, x plus 2. So that gives us zeros of 1, 3, and negative 2. That's where your 3 x-intercepts would be. And notice these last two numbers, those last two x-intercepts, also come from that list of potential integral zeros at the top. Our y-intercept, again, is the constant term. Positive 6 in this case. So for number 8, again, it's a third degree polynomial. The constant term is negative 1, which means we only have two numbers we're going to check, plus 1 and negative 1. So if we want to see if positive 1 is a root, we would divide by x minus 1, but let's change it to an x plus 1 so we can add as we're going along. And in this case, you've got an x cubed and x squared. There is no x term, so we have to include that with the coefficient of 0. And then we multiply and we add. 1 times 6 is plus 6. We add and get plus 13. 1 times 13 is plus 13. We add and get plus 13 again. 1 times 13 is plus 13. We add and get a remainder of plus 12, not 0. That means that x minus 1 is not a factor. So let's see if x plus 1 is a factor by changing it to a minus 1. Again, we do that so we can add as we're going along. One times negative 6 is negative 6. And we add 7 plus negative 6 is positive 1. 1 times negative 1 is negative 1. We add and get negative 1. Negative 1 times negative 1 is positive 1. We add and get our remainder of 0. So this tells us that x plus 1 was a factor. Also, the quotient, those three numbers at the bottom, give us the coefficients of the other factor, which will be a quadratic, 6x squared plus 1x minus 1. And that quadratic can be factored further. The factors are 2x plus 1 and 3x minus 1, which gives us x-intercepts of negative 1, negative 1/2, positive 1/3. And our y-intercept, again, is the constant term, which is negative 1. Number 9, a third-degree polynomial. But this one can be factored as a difference of cubes. If we want to know where x cubed minus 27 equals 0, this is a difference of cubes because you've got two terms and they're both perfect cubes and a minus sign in between. The cube root of x cubed is x. The cube root of 27 is 3. That gives you the terms in the first bracket. To get the terms in the second bracket, square the first term, multiply the two terms together, square the last term. And then you have to remember the sign pattern is minus, plus, plus. So you've got x minus 3 as one factor. That would mean x equals 3 is our first x-intercept. Our second ones will come from that quadratic. Once again, it cannot be factored. So we would use the quadratic formula. Negative b plus or minus the root of b squared. 3 squared is 9 minus 4 times a times c all over 2 times a. And in this case, once again, we're going to get a negative under the radical. It's going to be 9 minus 36, which is negative 27. Can't take the root of a negative number, so there are no solutions to that one. But we do have one x-intercept. That's positive 3. And again, the y-intercept is the value of the constant term, in this case, negative 27. Number 10 is a sum of cubes. If we want to know where 8x cubed plus 1 equals 0, we can factor that as a sum of cubes. The cube root of 8x cubed is 2x. The cube root of 1 is 1. To get those other terms, square the 2x, which is 4x squared, multiply the two terms together, square the 1. And the sign pattern for sum of cubes is plus, minus, plus. So from the first factor, if you make it equal to 0 and solve for x by subtracting 1 and dividing by 2, x equals negative a half is our first x-intercept. To check to see our second one, because it's not factorable, again, we'd use the quadratic formula. Negative b, well, b is negative 2, so negative b will be negative 2, which is positive 2, plus and minus the root of b squared, negative 2 all squared is 4, minus 4 times a, which is 4, times c, which is positive 1, all over 2a, which in this case will be 2 times 4, which is 8. And once again, we're going to get a negative under the radical. It's going to be 4 take away 16, which is negative 12. So once again, that tells us there's only one x-intercept. That's at negative a half. And our y-intercept is the value of the constant term, so that's positive 1, the point 0, comma 1. Okay? So we can use these as well as what we've learned about derivatives to help us sketch functions. That's going to be what we're going to be talking about for most of this chapter. We'll start with polynomial functions, then we'll get into rational functions and some different ones as well. So we can sketch this by finding the x-intercepts. It's where x squared plus 3x minus 10 equals 0. That can be factored, x plus 5, x minus 2. So that'll give us negative 5 and positive 2 as our x-intercepts. Our y-intercept, again, is the constant term, negative 10. So this is a quadratic. We know it's going to open upwards. It's going to rise to the left and right, which means there's going to be a minimum point. The vertex is going to be a minimum point. And we can find the minimum by finding the derivative. So our minimum point here will be where the derivative 2x plus 3 equals 0, the critical number of the derivative. So that's where 2x equals negative 3 or x equals negative 3 halves. So we're saying that that is a minimum. It has to be because the quadratic opens upwards. But we can confirm that, like we've been doing, by using our number line with our critical number of negative 3 halves. A number to the left of that, like negative 2, the value of the derivative when x is negative 2 would be negative 1, which confirms that the function is decreasing in that first interval. After negative 3 halves, a number like 0, when x is 0, the derivative is positive 3. It's positive, which means that the function is increasing in that interval. So that confirms that there is a minimum at f at negative 3 halves. And we can find out what that point is by letting x equal negative 3 halves in the original equation. It's a point on that graph. So we can use our calculator to help us here. In brackets, negative 3 over 2 all squared plus 3, and then in brackets, negative 3 over 2 minus 10. Negative 12.25 or negative 12 and a quarter. So it's going to be negative 3 halves, comma, negative 12.25. So there's my axes. I'm going to put a scale on here of 2. So that I can graph. I've got x-intercepts at -5 and +2. My minimum point is at -1.5, comma, -12 and a quarter. So approximately right there. So there's a sketch of our graph. Okay. This next one is a third-degree polynomial. So remember in 30-1 we learned about these polynomial functions. Because it's a third-degree polynomial, the degree is odd, we compare it to a line, which also has an odd degree. When a line has a positive slope or a positive initial coefficient, it'll fall to the left and rise to the right. All third-degree polynomials will act the same. Once again, the initial term coefficient is +1, so this graph will fall to the left and rise to the right. Our x-intercepts will be defined by letting y equal 0. So it's where x cubed plus 4x squared plus x minus 6 equals 0. And our potential integral zeros are plus and minus 1, 2, 3, and 6. They come from that constant term. So if we wanted to see if x plus 1 is a factor, which would mean that -1 is a 0, but we're going to see if x plus 1 is a factor by changing to x minus 1 so we can add as we're going. There are no missing terms in the polynomial. And all the powers are represented and they're in the right order. So we don't have to do any rearranging or adding any extra coefficients of 0. So now we multiply and we add. One times -1 is -1, we add and get +3. -1 times 3 is -3, we add and get -2. -1 times -2 is +2, our remainder is -4, not 0. So x plus 1 is not a factor. Let's see if x minus 1 is a factor. Again, we'll change it to x plus 1 so we can add as we go. One times 1 is +1, we add and get +5. 1 times 5 is +5, we add and get +6. 1 times 6 is +6, we add and get a remainder of 0. So now we see that x minus 1 is one factor. Our other factor is x squared plus 5x plus 6, which does factor x plus 2 and x plus 3. And again, we want to know where this equals 0. So that'll be where x equals +1, -2, and -3. So there's our x-intercept. Our y-intercept, again, will be the constant term, which in this case is -6. So next we'll find our intervals of increase and decrease, our local max and minimums. Our max and mins are where the derivative f prime x equals 0. So our derivative will be 3x squared plus 8x plus 1. That one cannot be factored, so we will use the quadratic formula. Negative 8 negative b plus or minus the root of b squared, which is 64, minus 4 times a times c, all over 2 times a, which will be 6. So that'll be negative 8 plus and minus 64, take away 12 is 52. We cannot simplify yet because we can only divide the first term on top and the bottom by 2. We can't divide the second term on top by 2. To do that, we have to write it as a mixed number, which we can do. Root 52 would be root 4 times root 13, or 2 root 13. And now we can divide everything by 2. We'll get negative 4 plus and minus root 13 over 3. Which, if we get as a decimal, because we want to graph it, it'll be approximately at negative 0.131 and 2.5, no, let me check these. Let's check these just to make sure. So, negative 4 plus root 13, all in brackets to keep our numerator together, divided by 3, at negative 0.131. And the second one is negative 4 minus root 13. Negative 2.54. So our x-intercepts are irrational. We'll have to check or estimate where they are. Our y-intercept, sorry, we've already done that. So here's where we'll use our number line to see which is a max and which is a min. So we've got critical numbers at negative 2.54 and negative 0.131. So a number to the left of negative 2.54, like negative 3. When x is negative 3, and we're using the derivative again, that's our 3x squared plus 8x plus 1. When x is negative 3, negative 3 all squared is 9, times 3 is 27, minus 24 is plus 3, plus 1 is plus 4, positive there, which means that the function is increasing, which matches that it's going to fall to the left. A number between these two critical numbers, a number like negative 1. Negative 1 all squared is 1 times 3 is 3. Take away 8 is negative 5. Plus 1 is still negative, negative 4. So the function is decreasing there. After negative 0.131, a number like 0, you'll get plus 1 there. So the function is increasing there. So we have a max, a local max at f at negative 2.54. And when x is negative 2.54, we'll get positive 0.9 approximately. We'll have a minimum at f at negative 0.131. And if you plug that into the original expression, you'll get negative 6.1 approximately. So that's really all we need to sketch this graph. We have x-intercepts at 1, -2, and -3. Our y-intercept is at -6. So here on the x-axis, I'm going to use a scale of 1. But on the y-axis, I'm going to use a scale of 2. Just because the numbers that we need to put on there. So we're going to have x-intercepts at positive 1, -2, -3. Our y-intercept is at -6. I've got a minimum point at negative 0.131, comma negative 6.1. So just below the y-intercept. I have a maximum at negative 2.54, comma 0.8, approximately right there. And this gives us all we need to sketch our graph. And there's our sketch. Okay? So for number 3, let's look at this one. Again, it's a third-degree polynomial. The initial term coefficient, though, is negative, so it's going to act just like a line with a negative slope. This graph will rise to the left and fall to the right, which means that that first critical number should be a minimum. As you're going right to left, it's going to rise to the left, so as you're going left to right, it's going to be falling. Right? Our x-intercepts, again, are where y equals 0, where negative 2x cubed plus 5x squared minus 2x equals 0. And this one can be factored by taking out a common factor of negative x, which will give us 2x squared minus 5x plus 2. And then we'll factor the quadratic that's remaining. It will be minus 2 there and minus 1 there. Front terms are 2x squared. The outer product is minus 4x. The inner minus 1x. That gives you your minus 5x. And the last terms are plus 2. So that gives us x-intercepts of 0, positive 1/2, and positive 2. The fact that 0 is an x-intercept, that means that our y-intercept is 0 as well. This graph goes to the origin, which there is no number at the end, so the constant term we could say is 0. Adding a plus 0 on the end doesn't change the function. Okay. So we've got that. Now we want to see if, or what our intervals of increase and decrease are. Our derivative, dy by dx, will be negative 6x squared plus 10x minus 2. And our critical numbers again are where that equals 0. We can take out a common factor of negative 2, which gives us positive 3x squared minus 5x plus 1. Now that quadratic cannot be factored further, the 3x squared minus 5x plus 1. So to see where the x-intercepts are from that, again, we would need to use the quadratic formula. The value of b is negative 5, so negative b will become positive 5, plus and minus the root of negative 5 all squared is 25 minus 4 times a, which is 3 times 1, all over 2 times a, which is 6. So that'll be 5 plus and minus the root of 25 take away 12 is 13. And because 13 is a prime number, we can't simplify this. But we can use our calculator to find out approximately where those x-intercepts are. So 5 plus the root of 13 in brackets all over 6. So that's at approximately 1.434. And I'm going to store that number into memory so I can plug it into the original equation to find out what the y value is there. So let's store this into memory slot A. And then 5 minus the root of 13 all over 6. 0.232, which I'll store into memory slot B. So now we'll use our calculator and we'll plug those values into the function. Well, actually, before we do that, we should use our number line. .23 and 1.43. A number to the left of 0.23 would be 0. And when we look at the value of the derivative, it's going to be negative 2 when x is 0, which means the function is decreasing. And that again matches what we said about rising to the left. So the function has to be decreasing in that first interval. A number between those critical numbers would be positive 1. When we look at the derivative and let x equals positive 1, we're going to get negative 6 plus 10 is 4. Take away 2 is still positive, positive 2. So the function is increasing in that interval. In the last interval, we can use positive 2. Let me check that again. Yeah, derivative is right. Okay, so positive 2. 2 squared is 4 times negative 6 is negative 24. Plus 20 is negative 4. Take away 2 is negative 6. So the function is decreasing in that interval, which again matches when we said that it rises left and falls right. So we're going to have a minimum at f at 0.23 and a maximum at f at 1.43. So now we'll go to the calculator. And we'll plug those values into the original function to find our points. So the point 232 we put into memory slot B. So negative 2 times alpha B cubed plus 5 times alpha B squared minus 2 alpha B. So that's negative 0.22 approximately. And memory slot A is where we put the 1.43. So we'll change all the B's to A's. Which is 1.5 approximately. And I've kind of run out of room to sketch this graph, but we have all the information that we would need to do that. Okay, so I'm going to stop there. We'll finish off this lesson tomorrow, talking about symmetry, and then go into lesson 2. So you can clear your desks for your quiz. The only thing you should have on your desk is a scientific calculator, not a graphing one.